All right, in this example, we've got a race car that accelerates from rest at a constant rate of 5 meters per second per second. Okay, that's what 5 meters per second squared. So it's accelerating, meaning that the velocity is changing by 5 meters per second every second. And it's doing this for 5 seconds. And we want to know how far the car travels and how fast it's going at the end of those 5 seconds. All right. Well, I'm gonna draw a little sketch of the velocity curve. Right. I'm interested in finding how far this car traveled from its starting point. So if I can find the area under the velocity curve, then I'm good. Right. So it's accelerating from rest. So at t equals 0, we're at 0 velocity. Right. And let's just draw in as 1, 2, 3, 4, 5. Let's draw in the little time scale here. Okay. So after 1 second, if I'm accelerating at 5 meters per second, then after 1 second, I'm going 5 meters per second. After 2 seconds, now I'm going 10 meters per second, right? That's what acceleration means, is that my velocity is increasing by 5 meters per second every second. All right, so then I'm at 15, and after 3 seconds, and so on. So you can kind of see that this velocity curve is a nice straight line, right? Because the rate of change is 5 meters per second every second. So I have a constant rate of change, which gives me a line. So here's 20, and let me draw 25 up here. All right, so you can see that after 5 seconds, I'm now going 25 meters per second, right? Because my velocity is changing at a constant rate of 5 meters per second per second. All right, so I can draw the velocity graph. It just looks like this. I'm just going to connect up these dots. It's a nice straight line, right? And we can actually write an expression for this line. The velocity is just equal to 5 times t, right? After 1 second, I'm going 5 meters per second. After 2 seconds, I'm going 10 meters per second, and so on. Okay. So if we want to know how fast we're going after 5 seconds, now we already figured this out just from graphing it, but we could also just say, well, we're going our velocity is increasing by 5 meters per second every second for 5 seconds, right? So that means we're going 25 meters per second at the end of this 5 second interval. All right. Now we want to find how far the car traveled as well. So I'm just going to draw a little dashed line here down to the 5. All right. So now we can do Riemann sums, but there's no real reason to in this case because it's a straight line. The area under the curve is actually just a triangle. All right. So the distance is the area of this triangle. And so we know how to figure out the area of a triangle. It's just 1/2 base times height, right? So the area of a triangle, triangle, okay, triangle. All right, let me back that up. Triangle is 1/2 base times height, okay? So, and that area is going to be the distance. So that tells me that the distance is 1/2. Now the base, I could consider this to be the base, the time axis, which is 5 seconds long, right? So my base is 5, and the height is this final velocity here. So this is 25, right? The height of this rectangle is 25 meters per second. Okay, so 1/2 base times height is just 1/2 5 times 25. So that gives me 62.5 meters. So this car has traveled 62.5 meters. So I found the area under the curve. I didn't have to use a Riemann sum. I just used the fact that I know what the area of a triangle is, and the area under this curve is a triangle. So it's the area between the curve, in this case it's a line, and the x-axis. That's the area we're trying to find. All right, so let's take a little deeper dive into this into this example. All right, so I'm going to just create a table of the acceleration, the velocity, and the distance over time. All right, so my acceleration is constant, right? So I can just fill this in. It's all constant, and I could graph that. It's easy enough. So down here I have a graph for acceleration versus time. Acceleration is constant, so it's just a flat line. All right, that's pretty boring. Now let's look at velocity over time. So at t equals 0, I'm starting at rest, right? And then my velocity is increasing by 5 seconds, or sorry, 5 meters per second every second. So after 1 second, I'm going 5 meters per second. After 2 seconds, I'm going 10 meters per second, 15, 20, and 25. That's what we saw above when we plotted the graph of it. Now let's take a look at how distance is changing with time. All right, now we're going to assume that we're starting at the reference point, and we're just measuring how far we've traveled from where we started. Okay, so, well, here, let me first of all, let's draw this the graph of velocity versus time, which we already did really, but so there's what it looks like. It's just a nice straight line. All right, so now to find the distance traveled after each time period, all we need to do is take the area. And they're all going to be triangles. So if I look at over the first second, this is going to be essentially 1/2 times 1 second times a height of 5, right? So the distance I traveled after 1 second is 2.5. After 2 seconds, I've got 1/2 times a base of 2 seconds, and I'm going 10 meters per second. So the distance I've traveled, the total distance I've traveled at that point is 10 meters. And so on. I can just find the area under the curve at these different points. So after 3 seconds, I'm going 15 meters per second. 15 meters per second. So that gives me 22.5. 22.5 meters is how far I've gone. All right. And I'll just keep going. After 4 seconds, I've gone going 20 meters per second. So that gives me 40 meters that I've traveled. And then finally 1/2 times 5. After 5 seconds, I'm going 25 meters per second. So I've gone a total of 62.5 meters. All right, and let's plot what that looks like. All right, so 0 at 0 and 2.5, so that's about a quarter of the way up. And then 10 at 2 seconds. And 22.5 at 3 seconds, so about there. And then at 4 seconds, I've gone 40. And at 5 seconds, I'm at 62.5, which is above the graph here, but I'm just going to sketch it in. It's about there. All right, and I can connect those dots. And you can see I get this nice curve. It is a nice parabolic curve. All right, now I don't know if any of you have taken physics, but you know that when you have constant acceleration, the distance is a quadratic, right? So we have this nice parabolic curve. So that's kind of what I wanted you to see, is that we can actually derive the formulas that you're given in physics if you've ever taken physics. You study the physics of motion. And they give you formulas, but we can actually see these formulas, and we don't even really have to be able to integrate yet. We just are looking at the areas under curves. All right. So if we have a constant acceleration, then velocity is equal to acceleration times time. Right. Our velocity at any given time is just the acceleration times the time. And if we look at the area under the curve at any given point, the distance as an area under the curve is just the area of a triangle then. So we have 1/2 v, which is the height of the triangle, times t, which is the base of the triangle. All right, now if we combine those, If we combine those two formulas and substitute, we can substitute this acceleration times time for velocity. And we get a formula. Distance is equal to 1/2 at squared, right? So essentially at times t, which is at squared, which is the formula you would get. They would tell you in physics. Now, this is, of course, assuming that your initial velocity is 0, right? And also that your initial displacement is 0. All right, so that's all I've got for you in this example. I just wanted to just see that for these constant acceleration problems that you do get the same formulas that you'll see if you take physics. All right, so I have a few more examples, and I'll meet you in the next video.